Thevenin's theorem. Let us try to understand Thevenin's theorem. What is it? What does it do? How can we use it? Consider an electric circuit like this. It has a source and a set of impedances like this. And it has a set of terminals called the output terminals. Let us call the source as V. It could be an AC source or a DC source. And I will use this arrow notation. You will be seeing this arrow notation frequently in AC circuits. What this actually means is that when you probe across this voltage source during monitoring, either using a CRO, oscilloscope or multimeter, it means that this is the positive of the probe and this is the negative of the probe. So that is what this arrow indicates. So we will call these impedances by some symbol names: ZA, ZB, ZC and ZD. And across the output terminals, let us connect another impedance called ZL or the Z load. Let us say this portion of the circuit, which is highlighted, is the fixed portion in this entire circuit network. The parameters are fixed. Whereas this portion shown green, the ZL portion connected across the load terminals, is a varying parameter. In such cases, if you use the mesh circuit analysis, then you will have to do the calculation for every value of ZL, you have to do matrix inverse and try to find out the branch currents and the node voltages. It can be quite cumbersome. Thevenin's theorem comes to our aid in such cases where we replace this entire fixed portion of the circuit by an equivalent circuit. So this fixed portion of the circuit is replaced by an equivalent, and we call that as the Thevenin's equivalent. And the Thevenin's equivalent circuit, which represents this network along with the variable portion of the circuit, would give essentially the same performance, the same voltage and the current values for this part of the circuit. Let us now use this highlighted blue portion as the Thevenin equivalent. It's a black box, it's a blue box here, and it has two terminals. We'll call that the output terminals, and across these two terminals we place the load impedance ZL, and this load impedance ZL is the varying portion of the circuit. Now this fixed portion of the circuit, entire fixed portion of the circuit, we replace by just two components. One is a source and the other is an impedance in series. We'll call the source by the name VTH, V Thevenin, and you could place an arrow symbol here to indicate the direction of the measurement. This means that you place the positive probe here and the negative of the probe here if you want to use an oscilloscope or a multimeter during measurements. And this impedance in series, we will call it as ZTH or Z Thevenin. Remember that if it is a plain resistance, it will be R Thevenin, it will be RL. Now this is the entire circuit network equivalently representing the active portion of the circuit which was fixed. Now if you consider these two terminals A and B, and across A and B is the output across which the variable portion is connected. Now if you measure VA to B, VAB potential is equal to, what is the potential here? It is the voltage across ZL, which is basically attenuated by ZTH. So VTH into the ratio ZL by ZTH plus ZL. So VTH into ZL by ZTH by plus ZL, like this. Now this is the relationship for the voltage across the terminals A and B, where VTH is the Thevenin voltage, ZTH is the internal impedance of the Thevenin source, which is ZTH. So these two are evaluated based on the active circuit, and for that active circuit these two will remain fixed, and then any values of ZL you can calculate using this relationship.